Welcome to another week of In Rhythm's Lightning Talks. This is your first time here. My name is Jen Crawford, and I have the pleasure of co-hosting this learning space. If you're new to Lightning Talks, they happen every Thursday at 5:15 Eastern. And it's a place where you can come feed your curiosity for technical knowledge by tuning in to learn from one of our amazing practice area consultants and grow with the phenomenal bar raisers that make up In Rhythm. This week, I'm very excited. We have the privilege of hearing from one of our lead software engineers, Dorit Benharush. During our time together, we'll be taking a pulse check on the level of expertise in the room. Dorit will help us learn and grow. We'll grab a moment of reflection for some community building, and then we'll close with some question and answer. So it seems like we have a good mix of some folks who know what supercomputers are, and a couple of folks who have joined us not really knowing much about it. So seems like everybody that's on the call here can definitely learn a little bit from Dorit. And so with that, I'm going to hand it over to her to get the party started. So Dorit.
Hello, everybody. And thank you for coming here. I'm going to close this poll or leave it outside. What should I do with this window? I don't know if you even see it.
Yeah, you can close it.
You can close it. Okay, fine. So I want to share with you some experience I have in model automation. And this is something I was really involved before I joined In Rhythm. And I found it very interesting topic. So let me just do some clarification about this topic that we ask what your knowledge base. The first one is supercomputer. And actually it's going together with all of this model. Supercomputer is when you take very big, when you have a big farm of many cores together. We can talk about thousands of core. It's not thousands of machine because machine on the cloud, they can have about 64 cores each. They are really strong compared to single 4, 8 that we run on our individual laptop, but they are very strong machine, and each core can have each individual calculation. So now I'm talking about running model that need thousands of cores, and it will take few hours to finish. And this is, I was working on the actuarial model, and finance company or insurance company need to show how resilient they are to any change in the market. Everything can go, everything can change in the market. I don't think anybody ran any model how the company will do in a pandemic time, because this is not even something that was in the to-do list before we started. But from now on, I'm sure this dimension will be added. But company, if you're an insurance company, you have to show that you are really resilient to any change in the market. So you have a list of what if criteria, and you need to show how your property or your budget will change from now on. And this is something that a lot of company must do it, because remember what happened on 2008 or another failure. So we don't want company that will be too big to fail. A company need to show how resilient it is. And this is where all the actuarial people come in place. And this report need to run monthly, quarterly, or year-end, depends on the requirement. Many regulations need to be accomplished by running all of this model. And where I was working, we try to go from running those model on a small computers that take forever to a situation that that is fully automated and run on the grid. And here's the challenge. Here is the challenge. So actuarial models are very big and they run on supercomputer. When you run them, most of the resources are not sufficient. You always need more and more and more because your complexity are getting stronger. On the other hand, when the models, this model can get complex all the time, but most of the time, models are not running and the resource sit idle. So we have to be, we have to balance all the resource. Another challenge was the ideal solution is automating the model execution while sharing resource between all departments. So this is involve a lot of politics because every department buy and spend the money for their resource. And they don't really like to share it because it came from their budget. So it's complex to tell people, like, look, if you share, yes, you will lose something that you spend money on, but on the other hand, when you need to run a big report, you will get much more power than you originally spent for. Another challenge that we face is everything can break, because to build something that is resilient and flexible and know how to manage all the error and all the failure, it's really complex. You have to think ahead about all the problems that can happen and build the logic to recover from it. So this was the challenge when we started the project. And our scope was that we need to automating everything, that we need to share resource between business unit with a different computational technology. And the idea behind it is that different departments need different technology to run the report. So we need the same machine to be able to run different computational technology. We also want to have dynamic provisioning. What's a big word here? We need everything to be dynamic. We want to use on this farm machine that sitting on premise in the company farm and also from the cloud. So we need to do mix and match between them. Something else we need in the scope, we need to manage queue. A job come, if there are all the resource, the job start. But what if there are not enough resource? Job need to wait in a queue. We also need to manage the inventory, and we need to manage the model specification. Last item in the scope was providing a live presentation from the model status, activities, error. So somebody from outside that submitted this job need to see what's going on inside. And I want to share with you, and I hope it's going to be clear because there are many, many components. This is a microservice environment to build all of this model automation that I described. And let me just briefly explain what it is about. So we have a job that submit to a job manager. And the first call is going to the provision. And we ask the provision, do you even have enough inventory to run this job? Because we tell it we need between 100 to 200 cores. So our desire is 200, but if you have 100, we are good. So first of all, is there enough capacity? If there is a capacity, we need to go, in this case, I just explained with Azure. So we need to go to the Azure and power on the machine. On the cloud, you pay only when you use. So you need to communicate with Azure and ask to power on. Then the next step is building a cluster. This machine needed to, the grid need to be built with them. They need to know so much about each other. So here we are building the cluster. Building the cluster, it's over here it was done with something that's called a command listener, because this stuff is Unix and that stuff is Windows. So we need something that execute all of those commands and build. And here I show two technology that's very common in the actuarial model. They have their own software. So this one called GGY and the other one called is HPC. HPC is very standard in the market for higher process computing. And we also need to build this cluster. So after the machine power on and we build the cluster and everything is done properly, now we have how it's called, we have like a template. The information coming back to the job manager, and job manager make a call to a different component to run this, this model. Now, funny story about it is, and everything built on the fly. So we build all of that with all of this component and all the error handling and everything. And a few years back, I was sitting on the HPC lecture in one of the AWS seminar. It was in the city, in the Javits Center, when we could go outside. And I was sitting next to somebody from, I think it was Deloitte or another big bank. And then I told him, you know, we are building cluster on the fly and we are sharing. He looked at me, wow, how could you do this? One, it's not built for this. Everything is static. And two, how could you convince all of these people to share their budget? At that point, I understood that we really did something good. Now, I know there are a lot of components here, so I have a different flow that show it a little bit more in detail, what we showed before. And maybe this is going to clarify some item here. So this is the job manager, and it make a call to this provision. If the provision have the resource, it make a call back. Yes, acknowledgement, I can do this for you. After that, it's going to the cloud API and power the machine. When the machine are on, we are going to the command listener and create all of those templates on the fly. And with the command, and then we bring back all the nodes and the two templates that was created. Then we execute the job and we wait until this job is done. And when the job is finished, we return the job status. That can take between few minutes to a few hours, depend how complex it is. After that, we start the deprovision process. And that's mean is remove the template with the PowerShell and power off all the machine and return the result back to the job manager and then back to the client. Actually, my mistake. When the job done, we are returning back to the client because client does not need to wait until we tear apart the farm. They know that this is done and they can go and check the status. I can go on. So here are a few obstacles and risks that we got while working here. The layer communication is extremely complex between everything. Model run involve many layers working together. We have the client, we have the orchestrator, we have the Windows, we have the cloud, we have the Unix. So it's kind of a huge obstacle here. Also, each layer is responsible for communicating to all other layers. if there is an error, so we need to know, should we apply a retry logic? How long can we do it? How many times we want to apply? And if it's not working, how do we notify the other layer? For example, we start on the first step and then we power the machine. Then we cannot build a cluster. Now we need to power off the machine. Power off belong to a different layer. So you definitely need to do a lot of like flow and every time check yourself and know what's going on. Another challenge that was, it's all the security between all the layers and the performance. Because if I'll go back, originally the plan was this take 10 minutes. Tearing it down take another 7 or 8 minutes. If you're talking about a big job that ran for hours, so another few minutes not going to kill us. So it's better to just build the farm, run the job, and then tear it apart. But it happened that some organization ran a big job. Other organization run many small jobs and then merge the result. So we need to be smart to know when do we tear apart, when do we leave the farm on idle that the next job can use it? Because if they run thousands of 2 minutes job, you cannot afford that each job will take 20 minutes for these 2 minutes that it's running. So there is a lot of game about it. Going live. So the Grid Orchestrator project changed the way actuarial models were run on for the company. Transition from manual run with limited resource to an automated process on a massive grid. Now, I just want, because I work now on AWS and everything going to AWS, so I want to show how do you run this project on the AWS. And it depends on what you run, because HPC is a kind of a standard solution. And here are the components that if you need to run an HPC job, what do you do? So we have the data, we have the file, we have the apps, and this is the S3 bucket. This is where you run the batch, big data run tool. Actually, just going in between the component and the result going to storage, but I'll read for you what is here. So we're uploading the scenario files and the calculation model to S3. The scenario is all the what if component, and the calculation is the brain behind the model. Then we are configuring the LWS batch using a launch template. We can use FSX technology for accessing S3 object as a file. Then all of these jobs result going are stored for a future audit. And then we are enabling all the logging into the CloudWatch. Because what happened is the government can come, or it can come as an auditor 3 months after and ask to see what was the job that ran 3 months ago and why the company showed this on the report. This is kind of internal audit and external audit. So we need to keep all of this information on file. So this is one option if we are running HPC. Another technology that was used is the GGY, and GG1 is specific software that the actuarial were using. Over here, we cannot use anything from what exists on HPC, so we need to build our own image and then start a cluster with all of this image. So create image with a GGY software for GGYQ and GGY workers. Then we need to create a cluster with those AMI, connect worker node to each GGYQ and server. So it's mean like, okay, we have the image, then from this image, we initiate machine, individual machine. Now we need to put them together so each one know about the other and they can exchange information. After that, we need to upload data to server and then launch the job. And that's it.